Okay, this is a lesson on paired samples hypothesis testing. This is the second question that we're going to go through, and we're going to try to go through this pretty quickly. So, a doctor wants to know if blood pressure medication is effective. There are 6 subjects who have their blood pressure recorded. After 12 weeks on the medication, the same 6 subjects have their blood pressure recorded again. For this test, only systolic pressure is of concern, and you should test at the 1% significance level. Okay, so here's what we're going to do. We've got the information right here, 161. We've got the blood pressure before, we've got the blood pressure after, and we've got all 6 patients. Okay, and so if you go to the decision-making tree, we're going to... Okay, so we have the decision-making tree here for hypothesis testing, and we have to ask ourselves a question. Are we dealing with continuous data from samples in a population, or are we dealing with frequencies, counts of categorical data? And we're dealing with continuous data, okay? So then are we examining the difference between a sample and a population, or examining the difference between groups? This is a little confusing because you're like, I don't know what we're doing. We're not looking at 2 different groups, but we are actually looking at 2 different groups. We're looking at a group of tests before taking blood pressure medication, and we're looking at the same group after taking blood pressure medication. And so we're examining the differences between the same group at 2 different times. Are the same participants being tested more than one time? In other words, do you have 2 values that are being compared? And the answer is yes. And so the next question is, how many groups do you have? Or categories of values, and the answer is 2. So we have before and after, and so now that brings us to the paired samples hypothesis test, and you can go through step 1 through 6 in order to be able to determine that. So I'm going to move on here. We now have the data, the before and after data, and the first thing that I'm going to do is I'm going to copy this data, Control C, and I am going to put it right there, okay, into Excel. So now I've got the Excel information, or the values all in Excel, and in just a minute we're going to calculate all of that. But let's go ahead and find out what is it that we want to know. What do I want to know? What I want to know is the blood pressure medication effective in decreasing blood pressure? Very simple. Is the blood pressure medication effective in decreasing blood pressure? And in order to be to communicate that, we need a null and alternative hypothesis in relation to this data. So when we have this data, right away we see there's before scores, there's after scores, and there's this fun little row here for difference scores. And we need to be able to calculate the difference scores in order to be able to write our hypothesis. So the before data, the after data, the difference scores. What is the difference for each individual person between before and after? So before minus after. So what I did here is I did equals before minus after. Before minus after. And then I just dragged it all the way down. And then right here, I'm going to get rid of these, but equals average. And just highlight everything that I want the average of, and drag it down. So now I've got the average of before, I've got the average of after, and I've got the average of the difference scores. And so for our null hypothesis and for our hypothesis, there's only one of these 3 averages that we're actually looking at, and that is this mean right here, the mean of the difference scores. And so the null hypothesis right here says the mean of the difference scores, or the mean of the difference scores for the individuals uh, being a participating in the drug study is greater than or equal to 0. So what does this mean? The mean of the difference scores for the individuals participating in the drug study is greater than or equal to 0. What this means is that the null hypothesis is saying that the difference between before and after, that the after score will actually be above the before score. That's saying that there is no difference. That's for the null hypothesis. And the reason why it's above is because when you have blood pressure medication that's effective, it lowers blood pressure. Okay. So now we're going to look at the alternative hypothesis. The mean of the difference scores for individuals participating in the drug study is less than 0. Okay, less than 0, which means that the blood pressure would have dropped as a part of the drug study. And so I've got to go right here and put those values in there. So I have all the values. I've got the mean that we calculated earlier. What is the level of significance? From earlier, we have the 1% level of significance. And then what is the test statistic? The test statistic that we need is a t-score. Why do we need a t-score? Because we only have 6 values. The only values that we're looking at are these 6 values right here, and that is it. So there are 6 values, which means what's the degrees of freedom? Degrees of freedom equals 5. So the degrees of freedom is 5, and so what's the critical value? That's a really good question. There's a few ways to do this, and I'm going to show you how to determine the critical value for a paired samples test. So a paired samples test for a t-score. What we can do, let's do it the most traditional way first. Okay, the way that we have learned how to do it, throughout class, and we're going to do t chart. Let's see here. Got the t-chart right here, and the degrees of freedom is 5. Right here, we've got the degrees of freedom of 5, and we've got a one-tail alpha, or a one-tail test, so it is going to be the intersection of 5 and a one-tail test. Okay, so 5 and a one-tail test. So that is 3.365. Okay, so 3.365 is one option that you can put in there. The other option is you can come right here and say, okay, I'm going to run a t-test with the data analysis tool. So I'm going to do a paired samples to sample for the mean t-test. I'm going to press OK. So the range 1, I'm going to have the before scores. Range 2, I'm going to have the after scores. The hypothesized difference is 0. It does have labels before and after. The alpha is 0.01, and then for the output range, I want it to be right down here, A18. We're going to press OK. And when we do this, it gives us the mean, the variance, the Pearson's correlation, the degrees of freedom. Then this is the actual calculated value of the t-statistic. Then we have the critical one-tail, the t critical for a one-tail test. So that gives it to us right like that. And then last but not least, we have an Excel formula. Okay, and the Excel formula is right here, t.inverse. So I'm going to copy this, and I'm going to put it right here. Okay, and I would put equals t.inverse, and then the probability. What is the probability that I want? Do I want 0.01? I don't know. And then the degrees of freedom. The degrees of freedom is going to be 5. So when we do that, the 0.01, the probability, it gives us the negative 3.36, which then you've got to determine, do I want it to be positive, do I want it to be negative? And so just make sure that you note that that's what it is, that you need to make it into positive or negative for your test. Next, the calculated value, like I said, it already gives you the calculated value right there. So you can use that, or you can actually use the paired samples formula to calculate it. But since we have software to do it, it's actually a lot easier to just do that. Next, I want to show you what we're actually looking at. Okay, what is it that we're actually looking at? What are we doing? We have, and I've got to make it a little bit, there we go. We have this distribution. This is the distribution of the difference scores. The distribution of the difference scores, the mean is 1.33. And this is a confidence interval. Okay, and for this particular confidence interval, I actually already did all of the calculations over here. So we have the mean of 1.33. We have the standard deviations of 1.86, which the way that I did that is I literally just did equals, if you look right up here, standard deviation sample, and I highlighted the sample, so the standard deviation, and then the standard error, I divided the standard deviation by the square root of the number of observations. Then the t-critical value, I got the t-critical value from right down here. And then I have the confidence interval t-value, which, note, for making a confidence interval, if I have a confidence interval, a 99% confidence interval, it's going to be in a different column than the one-tailed test. So you've got this column over here versus this column right here. So we have to have a different t-value. So the confidence interval t-value is 4.03. And then the margin of error is going to be 3.06. So I made a confidence interval around this mean to demonstrate that the mean of the difference. The mean of the difference of 1.33 is a point estimate, and we are 99% confident. We are 99% confident that the actual mean of the difference score is between negative 1.73 and positive 4.398. And we are testing it against this blue line. So I can already tell you that we are going to fail to reject because these yellow lines have to be outside of the blue line. So if this blue line is in the middle of these two, we already know right away we can't tell the difference. Okay, but there's a lot more to it than just that. And we're about to get into that. So I just wanted to show you this is the difference score line, and we're comparing it to 0. We are comparing the difference score, the point estimate of the difference score, we're comparing it to 0. Okay, so scrolling down, and I've got all the fun little formulas right here. And so let's get into the decision rule. So we have the decision rule, which is based off of the critical value. So we've got the critical value of negative 3.36493. And so the decision rule is we are going to fail to reject the null hypothesis if the t-calculated value, if our calculated test statistic is greater than or equal to negative 3.36. So if our t-calculated value is anywhere to the right-hand side of this green line, we are going to fail to reject the null hypothesis. However, if our t-calculated is anywhere to the left-hand side of this t-calculated value, this t-critical value, then we are going to reject the null hypothesis. So our t-calculated value is actually 1.754, while our t-critical value is negative 3.36. And this is not something that we've ever actually seen before. This is kind of unique, where we expected the blood pressure to go down, but actually the blood pressure went up. which is the exact opposite of what we expected it to be. So, did we determine that there was a difference? No, we definitely did not. We wanted to see, we believed that it was going to decrease blood pressure, but it did not decrease blood pressure. It actually increased. So the T critical value compared to the T calculated value, we definitely are going to fail to reject the null hypothesis. So let's keep moving on. So this is where we are deciding, what our decision is. Okay, and once again, we're going to refer back to the paired samples two-sample test that we ran in here, which is a really simple way to do it. But we have the test calculated value and the test critical value. So we've got to determine if we are going to reject or fail to reject the decision. The critical value is negative 3.36. The calculated value is 1.754. And so we're going to compare the two of these. And when we compare the two of these, we determined that the calculated value is less extreme than the critical value. Therefore, we fail to reject the null hypothesis, which is exactly what we write right here. Fail to reject the null hypothesis because the calculated value of 1.754 is less extreme than the critical value of negative 3.36493. Next, this is really important, okay? This is where you've got to actually do a little bit of math, but what is the p-value? What is the probability of this occurring, of this value occurring? This is saying, assuming that the null hypothesis is true, what is the probability of this occurring? And coming over here, you'll see two different p-values. You'll see a p-value of 0.139, and you'll see a p-value of 0.06989. And I'll tell you right now, neither one of those p-values are correct, because this one-tailed test assumes that you are going in the direction of the more extreme tail, okay? But we're actually going in the right tail or the upper tail. This is assuming that we're going in the left tail or lower tail. So the probability of what happened, the probability of the result that we got is actually equals 1 minus 0.06989. Because we've got a complement rule, right? If this is the probability of it occurring, if it was the one tail upper tail, if this is the probability of occurring if we expected it to go up. Okay, this is the probability of it occurring if we expected it to go down. And you add the two of these together, and it equals 1. Together. And that only makes sense, right? If you say, what's the probability of it occurring if you expected it to go down, and what's the probability of it occurring if you expected it to go up, the probabilities of the two of those together should equal 1. But the actual result that we got, we had a 93% chance of getting what it is that we got, assuming that the null hypothesis is true. And then the alpha of 0.01, therefore the results are not significant. Okay, and then we put in the fail to reject. Last, interpret your results. The doctor should know that the sample of 6 patients did not indicate that the medicine was effective in decreasing blood pressure. Conversely, the results actually indicated that the opposite was true. Well, not necessarily that the opposite was true. We don't know that it raised blood pressure, but the results actually indicated that the average differences between before and after taking medicine indicated a difference of 1.33, indicating that blood pressure was actually higher, not necessarily significantly higher, but it was higher after the medication. Also, another note is a sample size of 6 is very small. A sample size of greater than 6 should definitely be used for something like this. But either way, all that we can say is we can't conclude that it is below. We didn't prove that it's the same. We didn't prove that it's different. We just can't demonstrate that it dropped below. So that's paired samples. Hopefully that was beneficial. Like I said, there are additional practice problems after this. Hopefully those are also beneficial to you.